is another example we discussed previously. We'll try to understand that in a proper way. Yes, this stone was measured in air first. So the stone extends the spring and stops after some time. At this point of time, let me write the isolation diagram. I told you already, you'll think this mass is alone here, but don't forget the reactions on it. Weight is acting down. The tension, the pulling force of the spring is acting up. Call it T. So that T, since this thing is at rest, we write T minus mg equals 0, T equals mg. But the same T is pulling the spring again. I told you already, these forces T and T are action reaction, N and N are action reactions, Mg and Mg are action reactions. Never say Mg and T are reactions or T and N are reactions like that. So this T is the one which actually shows the reading. Yes, I remember we showed some, how many grams? 500 grams, for example, for this. So we are actually reading T, not Mg directly. Now you take it and put it in water. And our charismatic character Archimedes told that any body partially or fully submerged experiences an upthrust which is equal to the weight of the water displaced. That force is termed as force of buoyancy. Now, under the force of buoyancy, the weight and T1. I'll write a T1 here because once again this is coming to rest. A different tension will be there. In fact, this will be going up a little, making the spring a little less taut. Now we can write the isolation diagram for this like we wrote there, and we can write T1 plus B in the same direction we added, minus mg in the opposite direction we subtracted, and as a result of these three reactions, the stone is not accelerating at all. Its acceleration is 0. Therefore, T1 plus B minus mg equals 0 we wrote. T1 equals mg minus B. Previously T equals mg. That T is measuring exactly that mg. T is actually showing its own reading there, but that is accidentally is equal to the weight of the stone. That's the main idea. Now T1 will be once again acting on the spring balance, right? So that T1 shows the reading of some lesser weight, like I told you. I don't remember how much we told, 500 to some 350 went, I think. So it's showing some 350 here. So T1 is mg minus mg, and T1 therefore is less than our T. In fact, T minus T1, if I do mg minus B, that difference in the readings called weights is equal to force of buoyancy. I think now things are becoming slightly clearer. Yes, you can still say if you want, weight is a force applied by the earth on the body, but we should know that we will not be measuring it directly. We will be measuring it by developing another force. So what we measure as weight is not mg directly. What we measure as weight is some other opposing force. Don't say again reaction force to mg. That's not correct. Isn't it so? Now we develop another force, another contact force opposing this mg, and see that under this force the body comes to rest, and we measure that force which is equal to weight. But in case under the action of that opposing force, this and this mg together, the body is accelerating, the weight reading will change. What we call as weight reading will change. So these tensions, these ends, all these things are what actually we are referring to as apparent weight. Now, that interesting thing that astronauts feeling weightless in the satellites, that we'll address now. I want to remind you that the satellite or the astronauts are after all going in a circular orbit around the Earth because of the gravitational force. The weight, you may say, or g/m by r square, you might say, that is the force which is making the satellite and the persons inside change their tangential velocity direction every time and make it fall towards the earth, remember, everything is falling. The satellite would have gone like that, but it is made to fall into the orbit, not come and kiss the earth here. So from once again here it would try to go that way, but the gravitational force will make it fall like this. So every time the satellite which was going there is falling into the orbit, not falling, as I told you, and touching the earth. Yeah. So gravitational force is a reason for the such motion of a satellite or the person's inside. So this force becoming zero has no meaning, right? Newton called it a force, Einstein called it something else, but I told you already, I'm reminding you again and again, we are discussing Newton's gravity right now. Now, let us once again go to this person. This person is sticking to that roof. He is looking somewhat easy for our discussion. His weight is acting towards, weight means the force applied by the earth, mass of this person, some m1 I will say, into some g here. This g or g dash I will say, because g and the surface is different from the g here. It will be less definitely, but still we will have some that m1g force, m1g dash force on him acting towards the center of the earth, and he is supposedly sticking to that roof. So roof will push him back because he is trying to push the molecules of the roof. So the molecules push back. You may call it N on the person. Now we write the force equation for him. N plus m1 g dash equals m1 a. Look here, when the satellite is moving in the orbit, we write this force ma equals gm by r square. This mass cancels and g is gm by r square only. That means this a for the satellite or for the astronauts is once again g dash there, nothing else. So n plus m1 g dash is equal to m d dash. There is no other force to provide, make the acceleration different, try to understand. In fact, we are proving that this cannot be there. In fact, if the persons are going with the acceleration which is equal to acceleration to gravity, n has to be 0, we are trying to show here. So n becomes 0 here. So this n, the contact force is becoming 0. The satellite and the astronauts both are going around the earth with the same g. So that n cannot develop. That's what you mean by the astronauts floating in the satellite, and that's what you call the zero gravity situation. And yeah, the last example is still left. Let us address that thing. Now, near the equator, the person's weight is smaller, apparent weight is less than the real weight. Near the poles, it is equal, is what we have talked. Now, let us think that this person is standing on the measuring platform, okay, which has got a spring like this, and he's compressing the spring. He's compressing the spring with what, do you know? He's compressing the spring with the N. Try to understand. He doesn't apply his weight on the platform. Weight will be applied by the earth on him. But since he's in touch with the platform, he'll develop that molecular repulsion with which he's pressing the spring down. So there are, of course, the spring is, the platform is pressing him back with this N. So when you stand nearby him and watch him, you'll put one more force along with mg and n like this. Mg is the reaction of the earth, n is the reaction of the platform. Along with that, you will put another mr omega square. That's called centrifugal force, fictitious force, pseudo force. This is once again a troubling idea for many. 90% of the students and a large percent of the teachers just keep using some taken for granted notions about the centrifugal force and other things. But right now it takes longer time to clearly talk about it. That we'll address later. But let us say the centrifugal force is acting for a while. Now, as a result of these, of course, you know very well the centrifugal force or any pseudo force you put only to make Newton's laws valid in the non-inertial frame. Here the earth is a non-inertial frame because you are rotating along with the earth. There is acceleration for you, so you are in the accelerating frame of reference. Therefore earth is an accelerating frame of reference. To make Newton's laws valid, we introduce the pseudo force. That much is okay now, right now, because we want to explain why this person is at rest. So here mg minus n minus mr square is ma 0, because for you the person is not accelerating. So 0 you put this side and write the equation, and you finally get that n equals mg minus 1 minus omega square r by g, which is naturally less than mg. But remember, these two are completely different forces. They can be less or more depending on the motion of the object, isn't it so? Nothing is happening to mg as such, but n is measured by us as weight. Therefore we are saying that this apparent weight is less than the real weight mg, and that difference will be so much, mg into 1 minus omega square r by g. If you substitute all the known values, this approximately becomes 1 by 289 approximately, which is 1 by 17 square. Omega is known, r is known, g is known. The values if you put, it will be 1 by 289. But when you go to the poles here, you're not circling in any orbit like this. At the poles r equals 0. So therefore that when you write the equation for him, mg minus n equals 0, there is no mr omega square business there. Therefore mg equals n. That means the n you read by measuring the compression of the spring is actually equal to that weight mg, right? So finally, whatever difference in the weights we see are the measurement differences we make for n, t and things like this. Okay, and of course I'll tell you something else. In fact, the weight can become 0 also. For example, this value is omega square r by g is 1 by 289, I told, right? Now if you write n again here, mg into 1 minus, make this omega 17 times the present omega, 17 omega square by into r by g. If you write, it is mg into 1 minus 289 by 289, that becomes 0. N becomes 0. You will be losing touch with the earth, so you will be developing no contact there, and your weight will be said to be 0. I hope we have got some clarity on the definition of weight and weight as applied in many physical situations where it apparently changes. I'll try to summarize the results once again. Weight of an object is generally termed as the force with which the earth attracts an object. This kind of definition brings some kind of confusion later when weight of an object appears to be changing in various physical situations. Then we have to recognize that weight is measured only by developing an opposing contact force. And when we say weight is changing, we actually mean to say that N or the T, the other contact force which we developed against weight, that mg is changing. Okay, in fact that mg remains as mg itself, but the weight measurement changes. Hope the idea of weight is now clear to you, and I remember that we try to make it clear within the limits of F equals ma and F equals gmm by r square. Next time we'll discuss weight in terms of Einstein's principle of equivalence, that the effect of an acceleration and the effect of g in the local area cannot be distinguished from each other. Until then, goodbye.